Okay, I think we are live now. I hope you can hear me. Okay, yeah. Welcome to one more lecture of our of our course on heterogeneous systems. Today it's going to be the last lecture of the semester, and we are going to cover an important topic. We have already mentioned this topic in earlier lectures, but today we are going to cover it in depth. It's what we call collaborative computing. Before we go into the details, before we go into the discussion of collaborative computing, let me first very briefly remind you what we covered in the previous lecture. We talked about dynamic parallelism, programming style that can take advantage of dynamic refining algorithms. As you may remember, in the traditional programming model for GPUs, we have the host launching kernels onto the device for execution. And whenever a kernel finishes, it has to return the execution, it has to return the control to the host CPU. And this is going to be necessary every time we discover new work, right? We need to terminate the kernel, transfer back the control to the host, and then launch a new kernel. And this is pretty cumbersome and painful to implement. And this is where dynamic parallelism can help. Dynamically discovering new work that can be directly handled by the GPU threads, because these GPU threads now have the ability to launch new threads, launch new grids that will execute onto the device without involving the host processor. If you want to recap on dynamic parallelism and also on the performance considerations that we have to take into account for dynamic parallelism, I would recommend you our lecture 12, where we talk about it. In this lecture, by the way, we also talk about an important concept in the Cuda SDK, an important feature of Cuda, that are the Cuda streams. And now we are going to talk as well about Cuda streams as a way of optimizing the communication between the host CPU and the device or GPU, and how to handle asynchronous data transfers in order to handle this communication more efficiently. But very briefly, let's recall what are Cuda streams. Cuda streams are, but by the way, this concept also exists in OpenCL, and they are called command queues. These are sequence of operations that are performed in order. For example, in this sequence of operations, we can have data transfers and we can have kernel execution. If we don't use the streams, what will happen is that we will execute something like this. First of all, we will transfer from the CPU to the GPU, the input data, and then we will compute. In this figure, it doesn't appear, but after computing the kernel on the GPU, we'll have to transfer back the results from the GPU memory to the CPU memory. If we use the streams, and especially when we can use the streams to partition the computation, we can obtain some amount of overlap. The necessary thing to enable the usage of streams and asynchronous transfers and on overlapping is that we have some computation that is independent of each other. For example, if we have a certain number D of input data instances, the computation on these input data instances, or at least on parts of these, of the whole input data, is independent of other data instances or other parts of the input data. And if that's the case, we can divide the computation into a number of streams. And this means that we are going to divide the total number of input data instances D into smaller groups of data instances of size D divided by the number of streams. And also we will launch kernels executing a smaller number of blocks, in particular for a certain number of streams. It will be the total initial number, original number of blocks divided by the number of streams. So if instead of using the default stream, that essentially means don't explicitly use a stream in our code, we use several streams, we can obtain some overlapping between the data transfers and the execution. And also this could apply to the copy results or GPU to CPU transfers as well. And we can even obtain some raw estimates of how much performance improvement we can have by using these. And this will depend on what part of the overall execution is more dominant, whether the data movement or the execution. So for example, if the kernel is more, the computation on the GPU kernel is dominant over the data transfers, we will have that this computation on the kernel on the GPU will hide most of the data transfers. Only part, I mean, let's say like the first part of data that we transfer to the GPU to start the execution will add to the total execution time on the GPU. And we work on these Cuda streams and modeling the asynchronous transfers and the overlapping in one of our past papers. The way that we have to do this is, first of all, creating Cuda streams. We have to declare them as you see here, and then we have to create them using this API Cuda stream create. After that, we need to launch the data transfers for the input data from the host memory to the device memory. Notice that here we are using Cuda main copy async, which are a type of Cuda main copy that is asynchronous, and this means that it releases the host thread. The host thread doesn't have to wait for the completion of this copy, but it can continue issuing new copies as we do in this for loop here, and then we will start the execution of the kernel. Notice that both in the Cuda main copy async and in the kernel core, we are including the stream number, the specific stream number for each iteration of these for loops. And here at the end, we would have the GPU to CPU data transfers, as you see, in the opposite direction. At some point, we will have to synchronize. This is a Cuda device synchronize is a way of doing explicit synchronization, as you know, as we have seen in previous lectures. But there are also implicit synchronization considerations that you can check in the Cuda programming guide. After executing everything in our program, completing our program, we will destroy the streams accordingly. And as I said before, these Cuda streams and these asynchronous transfers and the possibility of overlapping communication and computation is especially useful in applications with independent computation on different data instances. For example, in video processing, it's very typical that we have to apply the same computation on different frames, but the computation that we have applied on every frame is independent on the computation that we apply on other frames. Or maybe we are processing windows of frames and the computation on each window of frame is independent of the computation in other windows. So if that's the case, then we can use Cuda streams, we can partition the computation and the data transfers on different streams, and this way we can obtain some amount of overlapping between the data transfers and the compute part on the GPU side. And thanks to that, we can save significant amount of time in some cases. We tested this as well as we came up with some, let's say, relatively accurate performance models for Cuda streams, and we tested this for a couple of video processing applications and also a few more applications in this old paper. And as you can see, for example, here for a 256 bin histogram calculation, here what we are doing is computing the histogram of each individual thread, each individual frame. Notice that how in two different GPUs, two different architectures, we can achieve performance improvements of up to 44%. And these are results for a different benchmark, in this case, RGB to grayscale conversion. So every single frame of the video is converted to grayscale. So if you want to learn more about Cuda streams and about overlapping data transfers and computation, you can read our paper, and also you can read section 18.5 in the Programming Massively Parallel book. Okay, so Now we are done with the Cuda Streams. That was kind of remaining thing that we still needed to explain better in this course and complete the, let's say, explanations related to Cuda Streams. Now we are going to go for the main focus of this lecture, that is collaborative computing. And we have, as I said in the beginning, we have talked about collaborative computing already in this course. Remember when we covered graph search in one of our lectures, and we talk about BFS, breadth first search, we said that the amount of computation in breadth first search, in every single iteration of breadth first search, might change from iteration to iteration, right? And that's especially normal in real world graphs, because not all nodes have the same number of neighbors, and we may have certainly some variability in the amount of nodes that we have to process in each iteration. And here you might remember this plot where we saw the frontier size, which is the number of nodes that we process in each iteration, how it changes over the course of the execution of the BFS algorithm on either a CPU or a GPU. In this case, in a let's say mobile platform like an NVIDIA Jetson that has relatively weak CPU cores and small number of GPU cores as well. And we saw that the performance of, or the execution time on CPU and GPU was changing relatively to each other, depending on what was the amount of computation, or what was the frontier size. And due to that, we said that a good fit here could be to have a collaborative implementation in order to avoid the small size frontiers to underutilize GPU resources. And essentially the idea is, in our host code, we will have something like this. We're going to have a while loop that is checking what's the frontier size at the end of every iteration. And while we have some nodes in the frontier, we will continue the execution. We will go for another iteration. But then, depending on what's the size of the frontier, we will execute the iteration on the CPU or on the GPU, right? And based on that, we obtain some performance improvement in some cases. Like, for example, in this Jetson platform, you can see here results for two different graphs. For one of them, we obtain like 15% performance improvement. For the other one, we didn't obtain any improvement, but the good thing is that the implementation adapts to the conditions of the graph, and in this case, most of the time is choosing the GPU, because the frontiers are pretty large, and that's why we see that the execution time of the collaborative implementation is essentially the same as the execution time of the GPU implementation. If you want to remind about graph search and about BFS, and also how we explain, or how we arrive to this explanation on the collaborative implementation of BFS, I can recommend you the corresponding lecture. But we are going to talk again and more in detail today about this implementation of BFS. But first of all, before we start, we need to understand what is the key feature that enables the collaborative execution, or the collaborative computing on different types of devices, or at least it allows us to do it in a seamless manner, in a easy to program way, and with some interesting performance improvements in at least certain important cases. And that feature is what we call the unified memory. But before we describe what's a unified memory, let me first remind you how we normally operate when we are working on the traditional approach, what we called in the past the accelerator model, where we need to explicitly allocate arrays, allocate data in the device memory, and we also have to explicitly move data using CUDA copy or CUDA copy async between the CPU memory and the GPU memory back and forth. This is a model that naturally matches systems with discrete GPUs, because in the end, when you have a discrete GPU, you have the CPU, the GPU connected to the CPU via some bus, like the PCI Express bus, and you have two physically separated memory spaces. So it makes a lot of sense to have to do this double allocation and this explicit data movement. Recall that the code would look like this, more or less. Here we have, we are first allocating on the CPU using malloc, then we allocate on the GPU memory using CUDA malloc, and then we copy with CUDA memcopy from the CPU memory to the GPU memory. We also have to allocate the output. We need to do double allocation, as you see as well, for the output in the CPU memory and in the GPU memory. And then we launch the kernel. After the kernel completes, we will have to synchronize the CPU and the GPU using this CUDA device synchronize. It's not really necessary if we are using here CUDA memcopy, because CUDA memcopy, as you know, is synchronous, but but we would need to use it if this data transfer is going to be asynchronous. But as you see, I mean, you're already familiar with this type of code where we need to do the double allocation in CPU memory and GPU memory, and also the explicit data movement between CPU and GPU memory back and forth. A way of making this easier is the unified memory. Unified memory appeared first as a unified virtual address space where the same virtual address space is shared by the host and the device. It first started in a, let's say, relatively simple manner in the Kepler architecture with CUDA 6.0. And back then, this unified memory, as we are going to see today, was already able to handle the data, the memory allocation and the data transfers transparently to the programmer, already saving a lot of effort to the programmers. But still, it wasn't a really coherent memory space that is seamlessly integrated for CPU and GPU. That started with CUDA 8 and the Pascal architecture, and what that is the it's the architecture where the GPU can start issuing page faults to the CPU whenever something is not found in the GPU memory space, in the physical memory space of the GPU memory. It can issue a page fault. The GPU can issue a page fault to the CPU, and the runtime system will handle the movement, will transparently handle the movement of the specific page from the CPU memory to the GPU memory. And one advantage of this is that now we are not restricted to, so when allocating memory on the GPU side, we are not restricted anymore to the available GPU memory, physical memory space, but we are only limited by the total amount of system memory. That's one advantage. Another advantage is that it's possible to maintain coherence between the physical memory spaces on the CPU side and the physical memory spaces on the GPU side, and some more features, like, for example, the possibility of using cross-device or system-wide atomic operations. So feel free to stop me if there are any questions. I will also keep an eye on the YouTube chat in case that there are any questions there. We have talked about the unified memory in the context of the NVIDIA GPUs, but that was not the only architecture that started to do more or less at the same point in time. Also, consortium, the Heterogeneous system architecture started to, proposed a unified memory space for CPU and GPUs and other accelerators as well, where instead of having like the classic approach where we have physically separated CPU and GPU, or even if they are physically integrated as we find in systems on a chip, and even though the memory space or the physical memory space is the same, they were still operating as completely independent devices, requiring double allocation and requiring explicit memory copies from the CPU memory to the GPU and from the GPU memory to the CPU memory. The HSA architecture, same as the unified memory in NVIDIA GPUs, allows to have a unified view of memory for CPU cores, GPU cores, and maybe other accelerators like DSPs as well. So essentially, the key concepts that we are going to explain in this lecture today apply to both NVIDIA architectures after the Pascal architecture, and after CUDA 8, and also devices from other vendors, for example, the AMD, that follow the HSA architecture. So remember how we have to program the system when we need to, or how we have to manage memory when we run a program with the traditional approach, where we have to do the double allocation and the explicit memory copies. We can save a lot of effort if we use a unified memory, because instead of using CUDA malloc and having to use malloc or other ways of allocating memory in the CPU memory, we can use a single API that is CUDA malloc manage. And with this CUDA malloc manage, we just need to allocate once. We don't have to allocate twice. In this specific example, you see that we are still allocating twice, but that's just because we are, let's say, creating the input data in some other array that is different from the one that the GPU is going to use. And that's why we are using this CUDA main copy here, but this is not really necessary. Whatever the previous function has created the data in input could directly on the CPU side operate on this D input allocated with CUDA malloc manage, because it's being allocated not in the GPU memory itself, but in the unified memory space. And same we do for the output as well. We allocate it with CUDA malloc manage, and then directly we can launch the GPU kernel, and at some point we will have to synchronize. Notice that in this case, we have to explicitly synchronize because there is no data transfer, there is no CUDA main copy. Remember that in the traditional approach, we may not need this CUDA device synchronize at the end of the execution if we are using CUDA main copy. But good thing is that we are saving lines of code because there is no need for double allocation or explicit data transfers. And this matches naturally, as we have actually seen in the previous slide, matches naturally physically integrated devices where we have the CPU and the GPU in the same chip, or devices with the same physical memory. The NVIDIA Jetson that I mentioned before is one example of this, where we have the CPU and the GPU in the same package. But this way of managing memory using unified memory can also be implemented for discrete GPUs. If we have the corresponding hardware and the, we have the necessary hardware and the runtime system. And we can even see that there are already some benefits, or we can see some benefits from using unified memory by directly replacing the traditional approach with the approach using unified memory without any sort of collaboration yet. Just simply saving lines of code, we may be able to obtain not only benefits in terms of programmability and maintainability of our code, but also in terms of performance. In this plot here, you can compare the execution time for different benchmarks. And actually for each of the benchmarks, we have two different versions. The D corresponds to discrete or traditional, that is not using unified memory, and U corresponds to unified memory. Here we are allocating using CUDA malloc manage, and we don't have to explicitly copy data from between CPU and GPU memories. As you can see, in some of the cases, there is performance is essentially the same for the D and U versions. In other cases, there is more communication, more interaction between the CPU side and the GPU side, and that's why the kernel time increases. But if we look at the whole picture and not only consider the kernel execution time, but also consider the data movement, the copy from the CPU to the GPU memory, that would be this red fraction of the bar, and from the GPU memory to the CPU memory, which could be this purple fraction of the bar, we see that there is significant performance improvement or overall performance improvement that can be achieved. Because here, for example, this unified version of this pad or padding benchmark, the execution of the kernel is hiding the data transfers. Of course, you could also, by the way, because in the beginning of the lecture, we talk about the asynchronous transfers and the possibility of overlapping computation and communication. Of course, it could be possible to achieve some overlap here among these data transfers and the kernel execution by using Cuda Streams, but that's more complex from the programmer's perspective, right? So it's doable, and you may be able to do it more efficiently than the runtime system itself, but yeah, for sure, more cumbersome and difficult to program. So we already see here some potential performance improvements that we can achieve from using unified memory. But we can go further, because this unified memory allows us to very easily implement collaborative applications. Before we talk about how to implement collaborative computing applications using unified memory, let me first remind you, or let me first discuss how we could implement collaborative applications with the traditional approach. In the traditional approach, it's not it's really not very easy, because it's more like take advantage of the CPU time while the GPU is doing something. And that's something we can do because the kernel launches are asynchronous. And what that means is that when the CPU launches a kernel for execution on the CPU gets free. It doesn't have to wait, same as it waits, for example, for a Cuda copy, the completion of a Cuda copy. It's a completely asynchronous operation. And what that means is that after launching the GPU kernel, the CPU can start doing some other stuff. So, for example, a different task. And this is, let's say, the way of exploiting heterogeneity and implementing collaborative computation in the traditional approach. After the CPU computes whatever it was assigned to it, then we will have to synchronize and then use the Cuda copy. Remember that we may not need this if this is because this Cuda copy is already asynchronous. It's already a synchronous operation. But as you see, it's quite cumbersome, and even if we want to apply this this pattern or this style of programming, we would need to know how much computation we give to the CPU here. And why is that? Because we also don't want the GPU to finish and then have a lot more of computation to do on the CPU, right? Or also we don't want to have like a very long GPU kernel and have the CPU computing something very small, maybe a couple of operations, and then just stopping here and waiting for the GPU kernel to finish. So in the end, tuning this way of implementing the collaborative computing applications is pretty challenging. So it's going to be much easier if we take advantage of the fine-grained collaboration that becomes possible with unified memory after Kepler and Maxwell architecture, in particular, since the Pascal architecture in NVIDIA and also in the HSA architecture. And why is that? Because this unified memory space already allows the GPU to launch page faults, and this is a way of implementing, or this can be used to implement memory coherence between CPU and GPU memory and what we call the system-wide atomics. And in this model, the main advantage is not only that we are saving the double allocation, and not only that we are saving the explicit memory copies that we had to do with Cuda copy or Cuda copy async, it's also that the CPU and the GPU can operate at the same time on the same arrays. And as you see here, we have only allocated one input, one output, and both the GPU kernel and the CPU are operating on the input and the output, and they can even use atomic operations as well on this data. So even if in some cases these may not provide the best performance, because in the end these page faults will require data transfers maybe over the PCI Express bus that is not extremely fast, or not so fast as the access to the global memory. It's definitely a really convenient way of implementing codes that exploit the fine-grained collaboration and fine-grained heterogeneity that we can have in many, many workloads. So in Cuda, the APIs that we need, or the key APIs that we have to use, or key functions that we have to use, are Cuda malloc manage to reserve, to allocate the space in the unified memory, and also the system-wide atomics. Like as you see here, these are this is the syntax of the system-wide atomics on the GPU side, and as you can see, it's actually quite similar to the original atomics in global memory or in shared memory. The only different thing is that we have added, or they have here, this system suffix to clearly identify that these atomic operations are in the unified memory. And it's not only Cuda that provides unified memory and systems-wide atomics. Since the Cuda 8, also OpenCL, since version 2.0, provides these features. Instead of calling it unified memory, they call it shared virtual memory, and the syntax is obviously different. Also for the atomic operations that here are called cross-device atomic operations or platform atomics, but essentially with the same purpose. And also for the HSA architecture, we can program it using a different programming language. It's C++ AMP. It's a higher level thing, but it still has like same features or same characteristics, unified memory space and platform atomic operations, or cross-device or system-wide atomic operations. So now we know, let's say, the basics of unified memory, memory coherence between CPU and GPU, and system-wide atomics, in order to start discussing how to implement like different collaborative patterns that we can find in real-world workloads. Before we start describing what are these possible collaborative patterns, let me very briefly remind you what's the traditional program structure. We are going to consider that the program is composed by multiple parallel tasks, and each of these parallel tasks can be divided into subtasks. So here you see one task that can be divided into, in this case, two subtasks. And we have a bunch of these tasks, a bunch of these data parallel tasks that can be executed exploiting data level parallelism on some multi-thread CPU, for example, or some GPU. At some point, we will complete these data parallel tasks, and following a bulk synchronous programming model, we will have to perform some coarse grain synchronization in the GPU programming model. This means terminating the kernel and then launching a new kernel, and in this new kernel, we will have new data parallel tasks, each of them composed by two or more subtasks. So the first way of taking advantage of the parallelism and the heterogeneity that we have here, I'm talking about heterogeneity because we have different tasks, and we have different tasks before the coarse grain synchronization and after the coarse grain synchronization, and we also have different subtasks that compose each of the individual tasks. So one way of exploiting parallelism and heterogeneity here is simply using data partitioning, which means that we are going to assign, assuming that we have two different devices, device 1 and device 2, for example, a CPU and a GPU, or a CPU and an FPGA, we assign some of the data parallel tasks to one device, the other part to the other device, then we will synchronize, and we will continue doing the same for the rest of the execution for the next kernels, right? The number of tasks that we want to assign to each of the devices will be dependent on what are the characteristics of the device, how much powerful for the specific task each device is. So this is like data partitioning pattern. But we can also do task partitioning. Why is that? Because we have different tasks and we have different subtasks as well. So the first type of task partitioning that we consider is what we call coarse grain task partitioning. In this case, we are assigning complete tasks to either device 1 or device 2. So, for example, in this case, we will have device 2 computing the whole first kernel, while after the synchronization, device 1 computes the whole second kernel. But observe that we have here subtasks, and it might happen that one device is better at one subtask and another device is better at a different subtask. So in this case, we can go even finer grain by assigning subtasks to different devices and communicating them in a fine-grained manner, assuming that we have that capability. And we are going to have that capability in today's systems because they support system-wide atomic. So as you see here, the collaboration is much finer grained. And in theory, if the overhead of communication of this fine-grained communication here that is represented by this dashed line, if this overhead is not too high, we will probably achieve the best performance with this fine-grained task partition. We can even analyze what's going to be the execution time of these approaches, and in this way, we could even have some estimates of what are the potential improvements or the potential speedups that we could get from a collaborative execution. To do so, in one of our papers, we did some analytical modeling where we consider a number of data parallel tasks. We consider the execution time of each individual subtask on each individual device, device 1 or device 2, the number of workers that we have in each device, device 1 and device 2. When I talk about workers here, I mean threads, CPU threads or GPU threads, or more specifically, the cores themselves. We may have, or we should consider as well, some overhead factor from doing the distribution and aggregation and so on, because in the end now we are partitioning the tasks and assigning them to different devices. So this requires some extra computation to do this distribution. We, in the data partitioning pattern, we are going to assign part of the computation to one device and another part to the other device. We are going to call alpha the fraction of data parallel tasks assigned to device 1. And in the case of task parallelism or task partitioning, what we have is a set of subtasks or a set of tasks that are assigned to device 1 or device 2. So let's first talk about data partitioning. So in data partitioning, we can estimate, or we can model the total execution time with this expression. In this expression, you can identify the total execution time for device 1, assuming that we have assigned a fraction alpha of the tasks to device 1, and this is the total execution time for device 2. Notice that this total execution time is for the sequential execution, and it's divided by the number of workers that we have in either device 2 or device 1. So the total execution time is the maximum of these two, right? And if we want to obtain what's the optimal alpha, what we have to do is make these two terms here equal, right? To make sure that the workload assigned to device 1 and device 2 are balanced. And if we do that, we will obtain an optimal alpha that corresponds to this expression here. In the case of the fine-grained task partitioning, we are going to assume, with like let's say simplified modeling, we are going to assume that the subtasks are very fine-grained and they can almost overlap perfectly. So in this case, if you have these subtasks assigned to device 1 and these subtasks assigned to device 2, because they are connected to each other, notice that in the end, the maximum execution time is going to be given by the maximum time for each of these subtasks. Either this green rectangle here or this yellow one. So depending on what's the maximum of these two, we will obtain the total execution time. And in the coarse-grained task partitioning, it's a kind of a similar way of obtaining the estimate, because yeah, we are assigning tasks to either one device or the other device, different sets of tasks. But in this case, we have to consider the whole computation on device 2 and then on device 1 or vice versa. And that's why we add the total times for each of the devices. There is no overlapping in reality here between the two devices. Okay, let's start discussing some use cases. Use cases or some, let's say, real world examples of these different partitioning patterns. We are going to start with data partitioning, and we are going to start with a pretty simple example that we already know, because we have covered in this course how to implement histograms on GPUs and also in other parallel devices as well. We start from here. So in the lecture where we covered the histogram computation, we were assuming that the whole histogram and the whole image and the histogram are processed by a single device, the GPU in that case. But if we have multiple devices in the system, we can somehow distribute the input images or divide the input images into different parts that are assigned to different devices, and this way potentially obtain some performance improvement. And that's what we want to do here in, or let's say, most naive approach to exploiting the collaboration between different devices. We can consider an input image like this and a system where we have several CPU cores and also several GPU cores as well. And what we do is statically partitioning the image depending on what's the amount of, how powerful each of the devices are. So here we assign this chunk of the image to the CPU cores and this bigger chunk of the image to the GPU cores. And because they operate independently from each other, we need to have separate histograms as well. One subhistogram for the CPU cores, one subhistogram for the GPU cores. This is completely independent as well of how we optimize the execution of the histogram calculation on the GPU. For that, I refer you to the corresponding lecture. But in the end, at the end of the execution of the kernel, we will have a histogram in global memory, and we will have another histogram in the main memory of the CPU. So what we have to do is merging them, right? So the way to do this with the traditional approach is we need to allocate the memory space for the corresponding part of the image on the CPU, the corresponding part of the image on the GPU. We have to copy the input image from the CPU to the GPU. We also have to double allocate for the output histogram on the CPU and the GPU. Then we launch CPU threads, and then we launch the GPU kernel that will compute the corresponding histograms. And at some point, we will get the histogram computed on the GPU back to the CPU memory, and then we will need to launch more CPU threads, or maybe have the main CPU thread merging the two subhistograms, right? This is doable, but as you see, it's relatively cumbersome. If we do a unified memory, we can at least save the, so if we apply the same approach using unified memory, we can at least save the explicit data transfers that we will have to synchronize in order to, right before merging the two subhistograms from the GPU and from the CPU. But this can be even easier to program, and we can save even more lines of code if we have a single histogram that is accessed by both CPU cores and GPU cores. And this is doable because now we have a unified memory space, we have a coherent view of memory from both the CPU and the GPU, and we can use system-wide atomics. And in this case, we just need to allocate one histogram, and we can launch CPU threads and GPU kernel, and using the system-wide atomics, we can complete, at least we can write the code in a much simpler manner. Of course, you cannot expect amazing performance of this implementation. This is just a simple example in order to start with the different use cases that we are going to cover. But in principle, we cannot expect very good performance here, because obviously these system-wide atomics are quite costly, because they are based on, at least on discrete systems, they are based on data transfers over the PCI Express bus, and that's quite costly. But this approach can be promising, for example, for systems, integrated systems or systems on a chip where we have a single physical memory space. Okay, your second use case is Bezier surfaces. We haven't talked about Bezier surfaces in the course, but in the previous lecture, we talked about the Bezier lines that are essentially the same thing, but one-dimensional instead of two-dimensional. In the case of Bezier surfaces, what we do is obtaining a surface that is controlled by a group of control points. In this case, we have a net of 4 by 4 control points, and depending on the relative position of the control points, we obtain the points of the surface. The way to do it is using the Bernstein polynomials that we mentioned in the previous lecture, and yeah, depending on the values of the control points, we will obtain the points in the surface. The computation in these Bezier surfaces, as you can see here, is relatively regular. It's not data dependent or something like that. So it's more the amount of computation for each point in the surface is the same. So here, some collaborative implementation that can work is a static distribution, a static partitioning, same as we did in the first version of the histogram that we have just discussed. So what we can do is dividing the whole surface into multiple tiles and assign different tiles to the different devices. In this case, the green tiles are assigned to the CPU, the yellow tiles are assigned to the GPU. We will need to do some, let's say, offline profiling first in order to know what's the amount of time that is needed by the CPU workers or the GPU workers to complete the execution of each tile or each point in the tile. But once we know that it's probably going to work well for every surface. And the way to implement this without unified memory is something similar to the generic code that we saw before. We first allocate in the CPU memory and the GPU memory the control points. We also have to allocate the output for the surface, and then we launch threads on the CPU side, and then and launch a GPU kernel on the GPU side. At some point, we will have to synchronize and then return the corresponding part of the surface computed by the GPU to the CPU memory. And with this approach, we can for sure achieve some performance improvement in some platform, like for example, in the NVIDIA Jetson. You can see here up to 17% speed up when assigning 20% of the tiles to the CPU. But with unified memory, as you already know, this will be easier to program because we will need less lines of code and saving the data transfers. But we can go one step further, and maybe it's something that, as I said before, here the computation is pretty regular, pretty stable in this specific benchmark, in this Bezier surface. But in other workloads, the amount of computation per tile, for example, might differ, right? Might be data dependent. And in those cases, it's really interesting to have some dynamic distribution, because in the dynamic distribution you don't need to know the best partitioning in advance, and what you can do is just go to a queue and fetch each of the workers whenever they are done with the corresponding tile. They go to a queue and fetch a new tile and compute for this tile, and this would allow us to have this dynamic distribution. And the good thing is that with the unified memory that supports memory coherence and system-wide atomic operations, it's possible to implement this dynamic implementation. What we will do is have the kernel body in a while loop that is running continuously until we break it. And in the beginning of the loop, in the beginning of each iteration, we will have one thread in every thread block updating one global variable that is updated atomically, and this is this tile num that tell us what's the tile, or tells this worker, in this case one thread block, what's the tile that needs to be computed. The rest of threads of the thread block are waiting for the thread 0 in this case to update this tile num and obtain the new tile to compute. This assume that this my tile is in shared memory, so it's visible to all threads. When the my tile is greater than the or greater or equal than the total number of tiles, we will break the loop and the execution will finish. If not, we go for the computation of the tile. And this implementation, it's pretty suitable for an integrated device, like or an integrated system, like it is, for example, this AMD Cavalry with 4 CPU cores and 8 GPU cores. And we see that with this data partitioning approach, we can achieve a performance improvement of up to 47% over the GPU-only implementation. Another use case is matrix padding. Matrix padding is a simple but very useful operation that can be useful for memory alignment on SIMD architectures, or for example, transposition of near square matrices. In matrix padding, as you may know, what we essentially do is adding extra columns to a matrix, right? This is going to be our output. I mean, this color part is the input matrix. After we add the extra column, this would be the output matrix. But now observe that the way that this matrix is stored, I mean, the way that this matrix is stored in memory is row by row, typically, right? So if we want to do the padding operation, we will have to reserve a little bit more space, right? Because these empty cells that we see here will be the cells that are added in the last column. And one problem with performing matrix padding in a parallel machine is that if we, for example, assign different rows to different workers, the operation will have to typically done out of place. What that means is that the output matrix will be stored in a different physical space as the input matrix. And this happens because when we move this row will go here, but then some of these rows here will occupy the space that was originally occupied by this bluish row, right? And if you don't have a way of synchronizing, at least synchronizing efficiently the different workers that you have in the system, then I mean, you may end up overwriting some of the rows, right? And this is a kind of a problem in modern systems where the amount of memory, or at least the amount of fast memory like DRAM, is relatively limited. And especially if you look at the amount of memory in GPUs, you will see that is even smaller than what we find typically in CPUs, right? So for GPUs, if we were able to implement some in-place implementation of matrix transposition, of matrix padding, it would be even better. But let's first assume that we are doing the out-of-place implementation of matrix padding in a system with CPUs and GPUs. So what we are going to do, because we are operating out of place, is that we divide the matrix into 2 parts. We assign one of the parts to the CPU threads, another part to the GPU threads, and then we have them moving the corresponding rows, right? And if we do that in the NVIDIA JetZone, we will obtain some performance improvement when, for example, 30%, this particular experiment, when 30% of the matrix is assigned to the CPU, right? You see up to 29% speed up over the GPU-only version. But we can implement an in-place matrix padding if we have the features in the unified memory, because in this case, we can synchronize across boundaries. We can synchronize different threads running on different blocks on the GPU side, and we can synchronize them with the threads running on the CPU side. And we can do that because we have atomic operations. So we can have kind of an array of flags in the unified memory that is accessed by both the GPU workers and the CPU workers. So the way we would do, let's assume that we assign here either to GPU blocks or to CPU threads, we assign to them different rows of these input matrix that is allocated as well in coherent memory. So this will be the final matrix, as you already know, and this is going to be the way that the matrix looks in memory, right? Where rows are stored one after the other in a row major layout. So if this is the physical space, the first thing we will start doing is having the workers from both CPU and GPU saving the rows in some temporary location, like for example in the CPU cache or in the GPU shared memory or registers. And these guys will start loading rows onto the temporary storage. And at some point, when some row is already completely saved in the temporary storage, we can have the corresponding worker updating a flag in order for other workers to know that this row, this bluish row, is already saved in the temporary location, and it can now be overwritten, right? So as soon as the flag is set, the CPU worker will start copying from the temporary location to the final destination. And this is how it's going to proceed, right? So here at some point, one GPU thread block finishes, stores or moves the whole row from the coherent memory to some temporary location. Now it sets the corresponding flag, and then it starts moving the row to the final destination without any issue related to overwriting other rows. And we can continue the execution until we complete the whole operation, the whole in-place padding operation. And you can take a look at some results here for this implementation on an AMD Kaveri. In this particular benchmark, we are not obtaining the maximum performance from more devices. As you can see here for this configuration with 16 work groups or thread blocks running on the GPU cores, we see that there is no performance improvement from using more CPU threads. It's different if we use a lower number of workers on the GPU side. In that case, we see some performance improvement related to the use of more CPU cores. But this is something that really makes sense for this particular workload. Why is that? Because padding, as you have seen, is essentially data movement, right? Is moving rows from one part of the memory to another part of the memory. So what we are essentially doing here is reading and writing from memory. And if we use enough number of workers on the GPU side, we would be already able to saturate the memory bandwidth. And actually, that's what we see here. For example, for these, the larger matrix that we tested, if we compare it to the bandwidth that we can obtain with the GPU stream benchmark, that is a way of measuring the peak bandwidth that is achievable or sustainable in a real system. We see that it's more or less, very similar, right? So what that means is that we are already exploiting here the available memory bandwidth, and using more workers, in this case CPU threads, doesn't really contribute anything but contention in the access to memory. Another interesting use case that also employs data partitioning is, or can employ data partitioning, is string compaction. I think we have already talked about the string compaction earlier in this course, but the string compaction or filtering is essentially a way of getting rid of data that we don't need in the input array and copying it to an output array that might be or can be in place as well, can be the same physical space as well if we have fine-grained fine-grained collaboration characteristics like unified memory, system-wise atomic, and so on. But the computation here is pretty similar to the padding, because it also involves moving data from some part of the memory to another part of the memory. There is a little bit more computation here because we have to check some predicate, and also we have to do some local reductions and so on. But yeah, it's a kind of a similar pattern to the padding as well. And here on the NVIDIA Jetson, using the traditional approach, we were able to achieve some performance improvement up to 25% over the GPU only implementation. And in the AMD Kaveri, we see the significantly higher performance improvement, up to 82% over the GPU-only version. And this, the implementation of a string compaction also works in place, same as the implementation of padding. Okay, so these are the examples for data partitioning. Now let's start talking about task partitioning, and we're going to start with coarse-grained task partitioning, and actually with a workload that we are already familiar with, that is breadth first search. Remember from the lecture on graph search that we talk about two different ways of implementing the BFS kernel. We had the kernel one that took advantage of a single thread block using the intra-block synchronization and avoiding the terminating kernel and relaunching new ones. That's something that would be needed for kernel 2, because there the size of the frontier was much larger, so we needed to use more or many more than one single thread block. The problem with that implementation is that after every iteration, we have to terminate the kernel and launch a new kernel, and this entails an overhead. And actually, I'm going to show you some motivational results in a couple of slides. But yeah, so we discussed how to do an atomic-based block synchronization that avoids this kernel relaunch. We are going to review this atomic-based block synchronization already today. Also today. Yeah, and also we talk about the collaborative implementation. We have started with that our lecture today, and here you have again the same plot for motivation, small size frontiers, underutilized GPU resources. So what makes sense is to process shorter or smaller frontiers on the CPU cores, while large frontiers are processed on the GPU side. And now the question is, how do we implement this, depending on whether we have a unified memory or not? So if we don't have unified memory, we have to follow the traditional approach. As you know, it will be more cumbersome to develop, more time-consuming, but we can definitely do it. So in our host code, we have this for loop with this while loop checking what's the size of the frontier. When the size of the frontier is smaller than a certain limit, a certain threshold, we will go for CPU execution. If not, we will go for GPU execution. What we have to keep in mind here is that we need to check what's the size of the frontier after each iteration. And what that means is that if we have computed on the GPU kernel, we first had to move data, the frontier, the queue containing the frontier and synchronization variables from the host to the device, from the CPU memory to the GPU memory. And after the kernel termination, we'll have to copy back from the GPU memory to the CPU memory, right? So it's something we can do, but it has the problem that we have these explicit memory copies. If we have unified memory, it's easier programming, simpler programming, because we don't have to explicitly copy between CPU and GPU memory. And this is something that would even work for Kepler and Maxwell architectures that they still don't implement the memory coherence feature between CPU and GPU. But in those cases, we will need to terminate the kernel and then do this CUDA device synchronize in order to make sure that the data is already available for the GPU, for the CPU to continue the execution. But one problem here, or the key problem here in this implementation, is that we are going to launch one GPU kernel for every frontier. And this requires to terminate the kernel and launch a new kernel whenever it corresponds. And that's actually quite problematic because of the high overhead of kernel relaunch. Launching kernels requires certain amount of time. If the amount of computation that you do later on the GPU is enough to amortize these kernel launch overhead, then we are fine. But in some workloads, like for example BFS, where there's not really so much computation, it's more like accessing memory to read one node and then visit the neighbors and so on. It's mostly data movement, right? And in these cases is where we can feel the or we can notice the overhead of every kernel launch and relaunch. And here you can actually see some performance results on a real system. This was also on the AMD Kaveri, the execution time for different graphs. So each of these corresponds to a single graph, and different configurations of the collaborative execution, from a version that uses only CPU thread to versions that use GPUs with different thresholds. For example, here, this 64 means that whenever we have more than 64 nodes in the frontier, we start using the GPU, or here is whenever we have 512 or more nodes in the frontier, we will use the GPU. So all these different bars and dots here correspond to different values of the threshold for the collaborative implementation. And what you can clearly observe is that the blue line that corresponds to the number of GPU kernel calls. Remember here, after each iteration, we terminate the kernel and launch a new kernel. So the number of kernel calls is completely related to the normalized execution time. And what we can observe here, and actually this happens for all configurations and for all graphs that we use in the experiment, there is no benefit from the collaborative implementation. So the collaboration is completely impractical due to this overhead of kernel relaunch on the AMD Kaveri. And this is where we can use our technique that we explained in the corresponding lecture, graph search lecture, the persistent thread blocks that avoid the kernel termination and relaunch. I'm not going to go into the details again, but essentially remember that instead of launching the whole number of thread blocks that we need to process the frontier, what we launch is only a number of thread blocks that can fit in the available resources and that can run concurrently at the same time on the GPU cores. And as soon as each of the thread blocks is done with the assigned part of the workload, it goes to the frontier and gets one more chunk of the frontier and continues the execution. And by using persistent thread blocks, it's also possible to implement atomic-based global synchronization across the thread blocks running on the GPU, right? And you might remember this code, the simplified code, and also this other simplified implementation of the global synchronization that required to have like a leader thread for the whole GPU and also one leader thread in each of the individual thread blocks. And by using this atomic-based block synchronization, we avoid terminating the kernel and launching a new kernel, which in the end is what is killing or was killing the performance in that experiment that I just showed on the AMD Kaveri. So, now what we do is launching the GPU kernel, but this GPU kernel will keep running while the frontier size still is greater or equal to the threshold or to the limit. And this saves a lot of overhead or avoids a lot of overhead from terminating kernels and launching new kernels. And this is something that we can do for the GPU kernel, and we also do it for the CPU threads as well. And this is how we managed to obtain some performance improvement on the NVIDIA Jetson. You're already familiar with this plot. For the New York graph, we obtain up to 15% performance improvement. But we can go even further. Why is that? Because in this implementation, even though we are avoiding the kernel termination in many cases, or at least while the GPU can continue or the CPU threads can continue the execution, because we are above or below the threshold, the number of nodes in the frontier. But we can go even further, because we wouldn't even need to terminate the kernel or terminate the CPU threads ever, right? These guys can compute when the frontier size is below the limit, or when the frontier size is above the limit in the case of the GPU. And whenever that's not the case, they simply don't do anything and just wait for their opportunity. Just wait to check after each iteration what's the size of the frontier, and depending on that, they will compute or not. And the CPU threads and GPU threads can continue running until the end of this while loop, until we don't have any more nodes in the frontier, and in that case, because we are using unified memory, we will need to use this CUDA device synchronize. But notice that now this CUDA device synchronizes outside of the while loop. And one more possibility that we have with this implementation is we can also have CPU threads and GPU threads working at the same time on the same frontier. Imagine that you have a huge frontier that where both CPU workers and GPU workers can compute at the same time. In that case, we could have like a second limit or a second threshold. Imagine that this limit is 64, for example, and now we can have another limit that is like, I don't know, 2048, for example. If we have more than 2048 points or nodes in the frontier, we would have both CPU threads and GPU threads working on the frontier. And now, by using this implementation, we can achieve some interesting performance improvements for some, not all, but not the largest one of the graphs. But for the smallest graphs, we can achieve up to 39% performance improvement over the GPU-only version on the AMD Cavalry. And here you can see these are the results for the New York graph. We see some actually more than 20% performance improvement for sure. The green bar is the GPU-only version, and this brownish bars with a pattern correspond to the collaborative implementation using different thresholds or different limits. And even for the Bay graph that where we didn't obtain any performance improvement in the Jetson, here we can observe some interesting speed up. And here you can see a few more results. This is related, it's not exactly the same algorithm. It's not BFS, it's a single source shortest path SSSP. That it's a related algorithm, has a little bit more computation, and in this case we can also obtain up to 22% performance improvement on the AMD Cavalry. Okay, and now let's move to fine-grained task partitioning. Is the last of the partitioning patterns that we are covering here. And for this one, we are going to talk about one interesting use case. It's an ego motion compensation and moving objects detection algorithm that was developed for an hexapod robot that was designed for rescue scenarios. And this robot typically moves over uneven terrains, right? And because it moves over uneven terrains and it has 6 legs, it's moving in a weird way, so it's difficult to have the camera stable, right? And if we want to do some processing of the images captured by the camera, we need to subtract, or we need to remove the strong ego motion. In a rescue scenario, it's important that the robot is able to to identify when someone is moving. For example, someone who was lost in the middle of the mountain is moving one hand. But if the robot is moving as well, unless we have a way of getting rid of the ego motion in the analysis, it's not going to be possible to find the moving object, right? And to do so, we used one algorithm that has like two different ways of finding the moving objects. It's like, and these two work synergistically. One is based on vector clustering, and the other one is based on frame differencing. We are going to talk about this branch of the algorithm here, and in particular about this Ransac algorithm that allows us to identify and create a model for the background. In the end, we start from in each frame finding what are the optical flow vectors that essentially represent how each of the pixels move from one frame to the next frame. And as you can see in this toy frame, this toy representation of a frame that we have on the slide, you can see that most of the optical flow vectors correspond to, are here horizontal, and they correspond to the background, while some other optical flow vectors that have a different direction correspond to this rocket that is flying here, right? So in the end, with this Ransac algorithm, what we want to do is obtaining a flow model for the optical flow vectors in the background. And the way that the Ransac operates is by identifying what's the main trend. As you see, the main direction in all these optical flow vectors is the horizontal one. So that's what the model is going to identify. And we're going to see how to implement this Ransac algorithm on an heterogeneous system. Here you can see some examples, some sample video. This is one of the videos that we analyzed, and here you can see the optical flow vectors for this specific frame. Most of the vectors, as you see, correspond to the background, and only a few of them correspond to the moving object. In this case, is the baby on wheels that you have here on the frame, and the clustering, the vector clustering algorithm will finally surround the baby with some bounding boxes. But let's take a look at the Ransac algorithm and how do we implement it on a how we come up with a collaborative implementation of it. So one interesting thing of the Ransac algorithm is that it has SIMD phases that are parallelizable or massively parallelizable, while it has other phases that are sequential or cis or inherently sequential, right? And this is the first stage in each iteration of the Ransac algorithm, is the fitting stage where we compute the flow model. Essentially, this fitting stage is as simple as picking two of these optical flow vectors randomly and generating a model. So if we obtain two of these flow vectors, we will definitely see that these flow vectors have the same direction, and based on that, we'll say, okay, most of the vectors of the frame have the same direction, and this is our model. And in the next step, what we do is evaluating how good this model is, right? We generate motion vectors from the model, and then we compare them to the real optical flow vectors. And based on that, we will obtain some score, and we will see if the model, the generated model, is good enough or not. If it's not good enough, then we have to go to the next iteration, and we will repeat the process until we have a good enough model, or until we achieve the maximum number of iterations that we want to execute, right? And as you see, there are CISD phases and there are SIMD phases here. So the way to implement this in a fine-grained partitioning manner is by dividing these whole task into several subtasks that are assigned to different devices. And the realization here is that all these iterations are independent. Why is that? Because the two vectors that are used to generate the model are randomly picked. And what that means is that we can compute multiple iterations in parallel if we have parallel workers, right? And assuming that we have a system with CPUs and GPUs, what we would do is assigning one iteration to a pair of one thread and one GPU block. And by using the fine-grained collaboration opportunities that the new unified memory provides, and the fact that we can communicate across devices using system-wide atomics, we can do this fine-grained synchronization. Whenever the CPU thread is done with generating a new model, it can signal the corresponding GPU block for the GPU block to execute the parallel part, SIMD part, where the model is evaluated, and after that, obtaining one score and returning the score to the CPU thread for the CPU thread to decide how good or bad the model is. Okay, so we have already covered the collaborative patterns and several examples of them, right? If you want to take a closer look at all these different examples and you want to access their code, I can recommend you to check the Chai benchmark suite. That is a benchmark suite that we developed for heterogeneous architectures and a collaborative execution of different applications. In particular, in the Chai benchmark suite, we have 8 data partitioning benchmarks and 3 coarse-grained task partitioning benchmarks and 3 more fine-grained task partitioning benchmarks. And we have different versions of them for different programming models like CUDA, OpenCL, and C++ AMP. We have versions for CPU and GPU, and we also have versions for CPU and FPGAs, and also for simulation. So this is the link to the website. And here this is a whole list of Chai benchmarks. Actually, you're already familiar with some of them, like, for example, Bezier, histogram, padding, Ransac, etc., and the different versions that we have. We have both, let's say, unified and discrete versions. Remember that the discrete versions are using the traditional approach where we have to terminate kernel and start a new kernel, and we have to explicitly move data from the CPU memory to the GPU memory, and vice versa. And then we have the unified versions that take advantage of unified memory, memory coherence, and system-wide atomics. And these benchmarks are pretty diverse, not only because we have the 3 different patterns, data, the fine-grained task, and coarse-grained task partitioning, but also because in each of the groups, they also have different characteristics. Like, for example, what is the partition data, whether it's the input, the output, or both, or how we are using the system-wide atomics. And also, even in the system-wide atomics, the benchmarks have like a strong variability of the intensity in the use of system-wide atomics for CPU, GPU, and these can represent interesting use cases for people wanting to do research on, for example, optimizing system-wide atomics on real systems. And the different workloads also have diverse execution profiles, as you can see here in these radar charts, where we show like occupancy of the different kernels and also different metrics obtained with the corresponding profiler about amount of cache hits or amount or memory intensity, compute intensity, and so on. And in our paper, we analyze all these different benchmarks and the different versions of the different benchmarks, the discrete and unified versions on an AMD Kaveri. And we can see that in the data partitioning benchmarks, the execution time, the kernel execution time is comparable in some of the cases where system-wide atomics are used. The unified implementation is a little bit slower. And then we also see that for the task partitioning benchmarks, the unified kernels can exploit more parallelism, and they avoid the kernel launch overhead. And here, these are the results for BFS, for example. You can see the large difference in execution time and how much savings we can have in the unified version that uses these system-wide atomics to synchronize across CPU, GPU, and this way avoid the kernel termination and relaunch all the time, right? And you see some good performance improvement here. And then the performance improvement is even better when we take into account the data movement that is needed in the traditional approach, either to move data to the device from the host memory to the device memory, which is the red fraction of the bar, and then return the results from the GPU memory to the CPU memory, and maybe do some final post-processing in the CPU side, which is this yellow fraction of the bar. So unified versions avoid this copy overhead. The only thing that we detected and we explained in the paper is that the allocation takes longer when using the shared virtual memory space or the unified memory in the AMD Kaveri. These results are relatively old, so for sure this allocation must have improved in later architectures, later generations. We also show in the paper a comparison between the execution on the AMD Kaveri for the OpenCL versions and the C++ AMP versions. You can check the details in the paper, and also if you are interested in this kind of application and also this kind of architecture, I can recommend you as well to take a look at this book, The Heterogeneous System Architecture, a New Compute Platform Infrastructure, and in particular, Chapter 8, to check some more use cases. As I said before, the Chai benchmarks are also available for FPGAs as well, and we have also been doing some work on fine-grained collaboration between CPU and FPGAs. Good thing is that in new FPGAs also new systems with FPGA also integrate features similar to the unified memory and the memory coherence between CPU and FPGA side, and these it's pretty convenient. First of all, because it avoids like having multiple versions of the data in a non-coherent memory space, which was a traditional approach. More and more, so vendors are starting to develop coherent interconnects for CPU and FPGA systems. Like for example, the CAPI or OpenCAPI is a newer version of the coherent accelerator processor interface developed by IBM and also other vendors in the same OpenCAPI consortium. And good thing is that now we can have a coherent view of the whole system for the CPU cores and for the FPGA, and save a lot of save copies of data, and also save a lot of time in launching the execution on the accelerator, moving data around, and so on. And that's not only for CAPI and OpenCAPI from IBM, also Intel systems with FPGAs provide similar features that allow to have a coherent view of the system between, or of the memory between the host CPU and the integrated FPGA. The key challenge is still to identify what's the best collaboration strategy, and that's one of the things that we did in this paper of us that we presented in ICP 2019. To program the Intel FPGAs, we had to use OpenCL, the OpenCL SDK for FPGAs, and we used two different evaluation platforms, both with a Intel Xeon host CPU, and then two different GPUs, sorry, two different FPGAs, both from Intel or from Intel Altera. And here you can see some results from one of our papers. In this particular case, or in this particular plot, we evaluated one of the CHI benchmarks, canny edge detection, that has actually data partitioning and task partitioning versions. And so in this plot, we are comparing the execution time for a CPU-only version, an FPGA-only version, and then the collaborative versions, either using that data partitioning or task partitioning. We can see that in both cases, the total execution time is quite similar. The key difference is that the host CPU can be idle or is idle like more than half of the time in both FPGAs, so in both systems with different FPGAs, and that's definitely something good, because it can allow us to move the CPU to other energy consumption levels that save energy, because it's in the end idle, not computing at all. And also for another of our benchmarks, Ransac or random sample consensus, we also have data partitioning and task partitioning versions. And here we see that in this case, task partitioning version is higher performance, because it exploits the natural disparity in task and the inherent heterogeneity that the workloads have. And if you want to go into the details, I can recommend you to check the paper, and also another recommended paper that also uses the CHI benchmarks and on FPGAs, in this case, to find what are the right optimizations to apply to OpenCL applications on FPGA. This is also highly recommended. We are not covering anything today about it, but probably in a future edition of the course we will talk about it. And we also have some good experience with the CAPI and OpenCAPI interface. We experimented with it for weather prediction modeling. We implemented accelerators on an FPGA connected to a Power9 system using the OpenCAPI interface. And this is Neuro, the Neuro application framework, where we implement some processing elements, some units that compute. This is a stencil computation way. I think we talked about narrow in the lecture about convolutions already. Here you can identify the accelerator, the narrow accelerator, and how the FPGA is connected to the host system using, in this case, CAPI2, but we also have an implementation using OpenCAPI, the most recent OpenCAPI. And this is the narrow paper, and this is the most recent version of the paper where we already show some results for OpenCAPI. So we are almost done today. Just let me remind you the key takeaways of this lecture. First of all, the possibility of exploiting collaborative computing, of having several devices, different devices collaborating on the same workload, and having the most appropriate cores for each workload or for each part of the workload, exploiting heterogeneity. We have seen different ways of implementing these collaborative applications using the traditional approach, but also using the easier programming with unified memory in NVIDIA terminology, or shared virtual memory in HSA and OpenCL terminology. This unified memory provides CPU, GPU memory coherence and system-wide atomics since the NVIDIA Pascal architecture and the HSA architecture, and this allows fine-grained collaboration, can report really interesting performance improvements for many workloads, especially in systems, in integrated systems, especially in those systems on a chip where we have a single physical memory space that can be accessed by both the CPU and the GPU, or maybe other accelerators at the same time. As I mentioned in the beginning, today is the last lecture of this fall 2021 semester of our Heterogeneous Systems course. All resources that we have used in the course and all lectures of the course are available in YouTube, and also the slides are available in our website. We will soon start with the spring semester around the end of February. We will have a new edition of the Heterogeneous Systems course where for sure we will cover new parallel patterns, and we will cover new details about the collaborative execution on FPGAs, for example. We may also have additional tutorials on FPGA programming. So yeah, keep tuned, because I think it will be very interesting, and we will even improve the contents of the current edition of the course. And together with this Heterogeneous Systems course, we have also similar courses. We call them project and seminars. We have another interesting one on processing in memory that I would definitely recommend you as well, because it relates a lot with heterogeneous computing, but in this case is in systems that have some sort of compute capability in the memory. So yeah, so all lectures and resources are available as well in YouTube or in our website. And these two are not the only P&S courses that we have. We have 5 more interesting P&S courses on SSDs, on memory systems, on bioinformatics, and you can access all resources from our website, and also from the Professor Mutlu's YouTube page, where you will find all the playlists corresponding to all these P&S courses, but also the undergraduate and the graduate courses on digital design and computer architecture, and also resources from the another course is a seminar in computer architecture that we have every semester as well. So this is all for today, and this is all for this edition of the course. I really appreciate your attention. I don't see any questions either in YouTube or in Zoom. So I think that I'm done from my side. Once again, to appreciate your interest. I hope that you find these lectures useful, and not only the lectures corresponding to this Heterogeneous Systems course, but also other lectures from Professor Mutlu and also other Safari folks as well. And I hope to see all of you in the next edition of the course that, as I said, in the spring 2022 semester will start around the end of February, and yeah, we will inform whenever everything is ready to start. Thank you very much.